Okay, so we will see the symmetrical problems now. Okay, a rolled steel joist of I section has the dimensions as shown in the figure. I will write. This beam of I section carries a UDL of 40 kN per meter run on a span of 10 meters. Okay, it is carrying 40 kN meter of UDL. Okay, with a span of 10 meters. Calculate the maximum stress produced due to bending. Okay, we have to calculate the maximum stress. So if it is a simple stress, we can directly find the sigma. Okay, if it is a maximum stress, we need to find sigma max. Okay, an I section. See here, this I section is a symmetrical I section. It is a symmetrical I section. It is not an non-symmetrical I section. Why? Because the top flange and the bottom flange both are the same width. Okay. See, the height of the I section is 400 mm. Width of the top and bottom flange is 200 mm. Top and as well as the bottom both are with the same length, 200 mm. Okay, thickness of the top flange and also the bottom flange are 20 mm. Width of the web is 10 mm and the height of the web separately given here. We can also find the height of the web separately. Separately we can calculate it like 400 minus of 2 into 20, that is 360 mm. 360 mm. So this is the diagram given. Okay, so this is a symmetrical diagram. The neutral axis passes through the geometrical center of the section. Geometrical center of the section due to the dimensions are, means the top and bottom dimensions of the section is same. If the top and bottom flanges are with different dimensions, as previously shown a figure like this. Okay, if the top and bottom flanges are with two different dimensions, then we have to find the CG. Okay, so this is an unsymmetrical section and this is a symmetrical section. Okay, so here the centroid is passing through, means neutral axis, and A is passing through the center, the geometrical center, means at 200 mm. Y max is equal to 200 mm. Okay, now so you can see the solution. So here UDL is given, that is 400 kilonewton per meter. We can also write it as 4000 Newton per meter, and the span L is UDL is 4000 kilonewton per meter, not kilonewton, Newton per meter, and the span L is 10 meters. Span L is 10 meters. Next, moment of inertia. Moment of inertia about neutral axis is equal to, width is, we know the formula, that is BDQ by 12. It is 200 into 400 cube by 12 minus of for the web, it is 200 minus 10. 200 minus 10 that is the width into the height of the web, 360 square. Height of the web is 360 square, cube, 360 cube divided by 12. So when we have calculated it, 200 into 400 cube divided by 12, that is 10. 1, 2, 3, 4, 5, 6. Minus, so minus 73872 000. Okay, so that is equal to 3279 466 m to the power of 4. Okay, so next is maximum bending moment. The maximum bending moment is m equal to WL square by 8. This is due to the UDL. M equal to WL square by 8. So W is 4000 into L value 10 divided by 8. It is I 50,000 Newton meter. Newton meter, or we can convert into millimeters. Why? Because moment of inertia is in millimeters. So 50,000 sorry, this is 5 lakh into 1000 Newton millimeter, which is equal to 5 into 10 to the power of 8 Newton millimeter. Okay, so now using the relation, we know one relation, that is m by I is equal to sigma by y, and in which sigma equal to m by I into y, and we need the maximum value. So sigma maximum equal to m by I into y max. Okay, so here we have calculated m, and bending moment we have calculated. Next I, moment of inertia, we have calculated, and y max is also known, that is 400 by the total height is 400, y max is 400 by 2, that is 200. Okay, so y max equal to 400 by 2, it is 200 mm. Okay, so maximum stress is equal to maximum stress is equal to m value 5 into 10 to the power of 8 divided by I value 32794 double six double six double six double six into y is 200. Okay, so we have to calculate it. So 5 into 10 to the power of 8 divided by 32794 double six into 200. It is 304.92 Newton per millimeter square. So this is the maximum stress occurred. So this is a symmetrical problem. So we have calculated directly the value of y. Have calculated the value of y directly. So if it is non-symmetric, means the flange sizes are different. If the flange sizes are different, then it is a non-symmetric section. It is a non-symmetric section. Okay, so you can see one non-symmetric problem related to I section, next to T section, channel, and some L sections, whatever is available. Okay, so you can see one by one. Now we can see a problem on unsymmetric section. Okay, a cast iron bracket, subjected to bending has the cross section of I form with unequal flanges. So unequal flanges means it is a non-symmetric. Okay, so dimensions are shown in figure. Dimensions are shown in figure. Find the position of the neutral axis. Okay, so so in symmetric it is very easy to find the neutral axis position, but in non-symmetric it is difficult, means we have to calculate it. Okay, so find the position of neutral axis, and then moment of inertia, about the neutral axis. Okay, so if the maximum bending moment on the section is 400 million Newton millimeter, then determine the maximum bending stress. Maximum bending stress. Okay, so that is the problem given. So we have to find the neutral axis, and it is a unequal flanges, means it is an unsymmetrical section. We have to find the neutral axis, moment of inertia, and the maximum bending stress. Okay, so sorry, the problem is like this. So top width 200 mm. Okay, top flange height 50. So all dimensions are in millimeters. Next, web width, sorry, web height 200 mm. Width is also same 50. Next, bottom flange width 130 mm. So top is with 200 mm and bottom with 130 mm. So both are different here. Okay, bottom flange height is also same, it is 50 mm. So this is the section given. Okay, so a cast iron bracket subjected to bending has the cross section of I form with unequal flanges. Dimensions are shown in figure. Find the position of the neutral axis and the moment of inertia about the neutral axis. If the maximum bending moment on the section is 400 millinewtons mm, then determine the maximum bending stress. Okay, so you can see, so given maximum bending moment is 400 million Newton millimeter, which is equal to 14 to 10 to the power of 6 Newton millimeter. Okay, so for this section we have to find the center of gravity first. Okay, we need you can find the CG. You can find the CG of the section. You can find the CG of the section. Okay, so y bar is the distance of the CG from the bottom face, from the bottom face. Okay, so here we have to calculate only y bar. So y bar is equal to, the formula, that is a1 y1 plus a2 y2 plus a3 y3 etc divided by capital A. Okay, so we know small a1 is the area of the first flange, or then area of the second flange, and a3 is the area of the third flange. So you can calculate it from the bottom. So a1 equal to area of bottom flange. So bottom flange width is 130 into the height is 50. So 130 into 50, so 10,000 millimeter square. Then y1 is the distance of CG of A1 from the bottom face. So distance of CG of A1 from bottom face. That is, so from bottom face, so from bottom it is 50 by 2, it is 25 mm. Next, A2, the area of the web. A2 is the area of web. So web height is 200 and the width is 50. So 200 into 50, 200 into 50. So this is also 130 into 50 is 6500 millimeter square, and this is 10,000 millimeter square. 10,000 millimeter square. Okay, and y2 is the distance of CG, distance of CG of A2 from the bottom face. So that is 50 plus 200 by 2. So 50 plus 200 by 2, half of the web height. 50 plus 200 by 2, that is 100 plus 50, 150 mm. Next, A3 is the area of top flange, that is 200 into 50, 200 into 50, it is 10,000 millimeter square. And y3 is distance of CG, distance of CG of A3 from bottom face, that is 50. So from bottom of the face, 50 plus 200 plus 50 by 2, half of the top range height. 50 plus 200 plus 50 by 2, that is 275 mm. So y bar is equal to, so top plane, bottom flange width A1, that is 6500 into height y 25 plus 10,000 into 150 plus again 10,000 into 275 divided by 1,500 plus 10,000 plus 10,000. So when we have calculated this, the value of y is equal to 166.51 millimeters. Okay, then we have to find the moment of inertia of the section about the neutral axis. Okay, so here we have two different sections. So we have divided the problem into three different rectangles. So we have to find the I separately for each and every rectangle, and we can add M R. So I equal to I1 plus I2 plus I3. I equal to I1 plus I2 plus I3. Okay, so we are here I1 is equal to moment of inertia of bottom flange about neutral axis. So we have the neutral axis. We have already calculated the neutral axis. So that is equal to moment of inertia of the bottom flange of bottom flange about an axis passing through its CG, plus A1 into distance of its CG from neutral axis whole square. Okay, so we have to find the moment of inertia with respect to the neutral axis. So for the first section it is 130 into 50 cube BD cube by 12 plus area of the first flange, that is 6500 into so distance of its CG from the neutral axis. Okay, so neutral axis is available here at a distance of 166.51, and we have to find the CG of the A1. Okay, so into 166.51 minus the area of first flange CG, which is available at half of the height, that is minus 25 square, so which is equal to so 131 51 71 86.6 millimeter to the power of 4. So this is I1. Similarly, I2 is equal to 50 into 200 cube by 12 plus 10,000 into 166.51 minus half Cg of the area from the bottom. Cg of the area from the bottom. So that is 200 by 2 plus 50. 200 by 2 plus 50. Okay, so minus half 200 divided by 2 plus 50 from the bottom. Okay, 50 whole square. 166.51 minus 200 by 2 plus 50 whole square. I2 equal to 33, 60, 59, 13.43 mm to the power of 4. Next, moment of inertia of the top flange. Moment of inertia of the top flange, that is same 200 into 50, so 200 width and 50 height cube by 12 plus A3 into so Y3 minus 166.51 square, so that is 200 into 50 cube by 12 plus A3 top range area 10,000 into Y3. Y3 is 50 plus 200, 250 plus half of the height of top flange, that is 25. Okay, so bottom flange height 50 plus web width 200 plus top flange height 50 by 2 is the Y3 minus 166.51 square. So moment of inertia we will not consider it in negative. So Y3 value is higher than the CG. So first we have written Y3, then CG. So this is equal to 11, 97, 84, 134.3 millimeter to the power of 4. This is I3. Now, so we need the moment of inertia I, which is equal to I1 plus I2 plus I3. So a bigger value. So 1315 1718 131718 6.6 plus 33 60 59 13.43 plus 11 97 84 134.3 equal to 2849 7234.9 millimeter to the power of 4. Oh, okay. Now, distance of CG from the upper top fiber is the total height of the I section. The total height of the I section is 50 plus 200 plus 50 minus of 166.51. So that is 300 minus 166.51, that is 133.49 millimeters. So this is 133.49 millimeters from the top fiber. From the bottom fiber it is 166.51. So which one is maximum? Okay, which one is maximum? Okay, and the distance of CG from the bottom fiber is equal to 166.51 millimeters. So which one is maximum? By maximum is 166.51. Okay, hence so we shall take the value of y is y maximum is 166.51 mm, okay, for maximum bending stress. Now using the equation same, m by a equal to sigma by y, or sigma maximum is equal to m by I into y maximum. Okay. 40 into 10 to the power of 6 divided by 28490. I value 28490 7234.9 into 166.51. 166.51. 40 into 10 to the power of 6 divided by 284907234.9 into 166.51. It is 23.377 Newton per millimeter square. So maximum bending stress is 23.377 Newton per millimeter square. Okay, so here in this problem the stress will be compressive. In case of a cantilever, if it is a cantilever, upper layer is subjected to tensile stress, whereas the lower layer is subjected to the compressive stress. Okay, the lower layer is having compressive stress. Why? Because the neutral layer is available from the bottom with maximum height. Okay.